I'm Francis Buontempo. I edit the ACCU's Overload magazine, so I've put Overload's email address up for anyone who feels inspired to try and write up how they might attempt to program their way out of a paper bag. Some of the code's up on GitHub. There's some other examples of some machine learning algorithms that I've used, but today we're concentrating on evolution. I'm going to keep kicking things. So I'm going to talk about what evolution means in the sense of computing. I'm going to stray away from Darwinian questions and biology and things I know little or nothing about. I'm specifically going to give you two examples. I'm going to work through genetic algorithms. If you already know loads about machine learning, you'll probably know about this. So just come out with a simple example just to introduce you to the basics of what you can do and the kind of things you can think about there. Then I'm going to walk us through an example of something called artificial life. I know we should probably mention testing, because testing is a good thing, and actually this is pertinent to the talk. And then we're done, and then I can have a pint of Guinness, which will be great. I will wonder if we can automate absolutely everything, including the code generation. There isn't time to go into that in depth. So, what's the background to this? Ages ago, someone came out of an interview, one of my colleagues, and said the candidate couldn't even program their way out of a paper bag, which is a phrase I think several people have used on several occasions. And I started wondering, what does that actually mean? Could I demonstrate I can code my way out of a paper bag? Could they demonstrate this? What does a problem even mean? It's very underspecified. Does the bag move or not? Loads of questions here. Now, I did my PhD in data mining and machine learning, so the obvious thing to do is to make a list of all the machine learning things I could think of and apply what's called a decision tree induction algorithm to the data I'd mapped out. I used one called C4.5, which is freely available from the RuleQuest website, and my massive table of huge amounts of different kinds of machine learning squashed right down to saying, if it did something slightly random, it might just work. So there's a few examples of previous offerings out there, including some in Overload. I am going to trip over that if I'm not careful. So today we're going to talk about evolution, particularly in terms of, well, computer programs and what kind of things you can do as you evolve something. Something evolves, it starts somewhere, and it ends up somewhere else. Not necessarily where you think it's going to end up. The motivating force behind this change that starts going on is, of course, mutation. Now, in terms of computing, we're mimicking what we think is going on in the real world. But we do this anyway as we write code. If you're confronted with, for example, a legacy code base, you've just joined a team, one particularly useful thing to do is scratch refactoring. Change public to private, and then you can start seeing the dependencies between things. Just get your hands in, start randomly changing things, see what happens. But you need one extra step there, so we're moving forwards, we're mutating things, but if you're trying to solve a particular problem when you're doing, say, for example, the scratch refactoring, you've got something in mind you're after. In terms of genetic algorithms and most machine learning algorithm situations, you have something called the fitness function, the thing you're trying to achieve. You need to measure whether the refactor you've just done was any good or not. Sometimes you can just go, yep, that was good, or no, that was bad. That works for you sometimes. So some kind of Ubermensch thing. Oh, I like my comics, I couldn't resist it. I also like some alternative music, so I also couldn't resist the Halbermensch from Einstürzend und Neubauten. Sorry, forgive me. At that point, so something can either be good or bad, and sometimes you can get a scale, some kind of numerical scale for fitness. So we're going to see a lot of mutation and fitness going on in the course of this, recurring themes. So my first example to code my way out of a paper bag is going to be based on genetic algorithms. Before I get there, the history of this stretches right back to the beginning of computation. If you look at some of the things Turing was trying to achieve, he was definitely after trying to build computers as a form of artificial intelligence. We'll go more into what that might mean in a moment. I think he just wanted to build a machine that he could play chess with, really. I think that was his overriding thing there. If you're trying to build something that's an artificial intelligence, do you do it by building a machine that mimics a brain and then see if it ends up being intelligent or not? Or do you do something that you say, well, I can't tell the difference between whether I'm playing chess against a human or a machine? So you end up with this divided opinion where the people who are trying to build a brain that is intelligent are the hard AI people. And Turing's approach was more what gets called the soft AI approach. And that's part of the essence of the Turing test. Can I tell if it's a machine or a human? It doesn't matter whether it's actually built up like a neural network with cells. Just if it plays chess or has a conversation with me on the internet, that's okay. It's exhibiting intelligence. There are different ways of doing this. And I couldn't resist just mentioning some of the other things Turing got up to. In terms of looking at building life and how it all works, he spent a lot of time looking at how zebras get their stripes and how other patterns form on animal skins. And there's some simple maths in there as he used, a nice simple model to grow the types of patterns you've got that's based on diffusion. I talked about diffusion last year, so I mustn't distract myself too much. Note to self, we're going to come back to genetic algorithms. I'm going to use an example of ballistics. It's just going to have two parameters to keep it nice and simple. And we'll think about possible extensions, maybe setting fire to the bag, or, as you were, kick the thing again. So, as I said, I just wanted to throw in the mention of some of the other work Turing was doing. So, if you build a reaction diffusion model, and I haven't put the maths up here, you can look it up yourselves, you get quite a convincing zebra-type pattern there. You've got the black bits moving and the white bits moving, and as they collide, it changes whether they're black or white. And there's some hand-drawn pictures up on the Turing archives of how you can get circles as well. So go away and look at this. It's really quite interesting. And again, the theme that's in the two topics I'm looking at today is nice, real simple rules that actually let some quite big, beautiful, exciting things happen. Simple is good. So, as I said, we can get the circles as well as the lines. So do check out the Turing archives. Got nothing to do with what I'm supposed to be talking about today, but I couldn't resist. A whole archive of loads of his hand-drawn things and little bits of math scribbles down the side where he's trying to work out a formula that will give you these kinds of patterns. Real beautiful things. Anyway, so back to what I'm supposed to be talking about. As promised, ballistics, which if we did them properly would set fire to the bag and get rid of the problem, which would be one approach. But I promised myself I wouldn't set fire to anything today. So, tiny bit of physics revision. If I've got a particle in a bag, two-dimensional, doesn't matter what colour the bag is, I don't think. If it was white, I wouldn't be able to see it, so we need to make some sensible and arbitrary choices here. If I launch it, I have to choose what angle I launch it at, and by convention, we'd start 0 degrees here and count round as we go round anti-clockwise. Doesn't matter. So I just want a number, and then I give it a velocity. And that allows me to work out the x-coordinate, how far across it is, and the y-coordinate, how far up it is after time t. So I can sample this every 10th of a second and see what happens. It's going to be pulled back down again by gravity if I do the experiment somewhere where there is gravity. So as an extension, we could do it where there's no gravity. For this experiment, I'm going to assume we're on Earth with our two-dimensional paper bag. So I'm going to pluck a magic number out of the air in the code for this. About 9.81 is about right. So I've got a simple model that's going to simulate things flying off in all directions. We want some of them to get out of the bag. Well, as many of them as possible to get out of the bag, hopefully. And we're going to use genetic algorithms for this. So, said I want an angle and a velocity. And just pick some random numbers for those and build up a population of these little ballistics that I'm going to fire off. So just do something random to begin with, see what happens. So, launch them, and then I want to build up a next generation based on what I found out in the first generation. I'm going to take some of the better ones and combine them. I'm going to perform some mutation. We mentioned mutation as being the thing that can drive us to explore new places. And then I need my idea of my fitness function to work out whether it was any good or not. Nice and simple. So, random starting point. I'm going to need to decide how many pairs of angles and velocities I want. I suggest more than 0 is a good idea. More than 1 is quite a good idea. 1 might work because the mutation can find things, but it might speed things up if I try more than 1. The paper bag, I happen to have made 10 units by 5 units. And this one's grey. Again, I don't think the colour is pertinent. And just launch them, see what happens. And with the random choices I've made in this particular example, you'll see some go up quite a way and don't get out. Some don't go up very far at all. Some go up a long way and then go back in again, which is mildly disappointing. But based on previous experiments, this happens to be surprisingly often. But some of them manage to get out. I've banned them from going out of the sides of the bag. You could argue I shouldn't have done that. You could argue that, well, maybe there's a critical point, and if they were going fast enough, they'd go through the bag. You could start arguing that if they went really fast, it might start moving the bag, and this is far too complicated for me, so I thought to keep it simple and then not going out the sides of the bag. So I've got some initial ones. Some get out, some don't. So start. So just some Python code, going to choose an angle and a velocity. Do you get that thing where you look back at some code you've written and think, what on earth was going through my mind? Now, so theta, the angle, I've chosen between 0 and 180 degrees. I don't want it to try and go through the bottom of the bag. That makes sense. Then for reasons best known to myself, I've chosen a velocity of up to 20. Okay, fine, 20. I cannot for the life of you tell you why I chose 2 as the lower bound on that. 1 would probably have been okay. If I'd chosen 0, I know that it's not going to go anywhere. But the fitness function is going to flush that out anyway. So I should probably have just started doing not 2. Terribly sorry. Anyway, so get these pairs, build them up into a generation, launch them, see what happens. Now we come to the mutation and the crossover and the fitness part. From that first go, and all genetic algorithms follow the same structure. You just do something initially with random choices for your variables. The more complicated case can have more than just 2. I chose 2 to make the crossover really easy to describe, as we'll see. And from this, I'm going to build a new generation. There's lots of ways of building up the new generation. The simplest one is to just put the old one on the side and start a complete new one. I'm going to choose some of the better examples from the first one. So in the picture we saw just now, some of them got out, some of them didn't. So the simplest thing I can do is just find some of the ones that got out. Then I can cross over the information, the analogy being like the DNA strands combining from 2 parents. But if you're doing genetic algorithms, you don't need 2 parents, you can have 3. It's just then a combination game, see what happens. Then I can maybe mutate the parameters to make the velocity slightly bigger or slightly smaller, or likewise with the angle. Run it again and just keep running around. So I'm just going to have a for loop and try for a bit. You can choose in advance the number of times you're going to do this for. You could let it run until it solved the problem. You could let it run until you just hit a key because you were bored with it. You let it run until it finds one solution. Same shape. Randomly set things up. And then build new generations by this crossover and mutate that I'll go through properly in a moment. And fitness helps us choose what we're going to cross over. And then hopefully we move towards a better solution. So that fitness function, or Übermensch or Halbermensch again. I'm going to show you two examples. The first, simplest idea of just see if anything's escaped or not, didn't work out very well, but it's okay to try something and not succeed, and it's really good to tell other people what you've done that went wrong. It saves them making the same mistakes. Like I said, there's choices about what you do with the generations, but I'm just going to do a simple thing. One initial random thing, sweep them aside and rebuild a new generation each time. You can do variants on this. You can take the best ones each time. You could just kill things off if they're worse, or if they've lived for more than 3 generations, or you can think of as possible. There's no one right way to do this. Once you've got the basics of the algorithm, you can play around with it and see what happens. And the particular problem you're trying to solve, there'll be some things that are better than others. Better there tends to mean finding a solution quicker, but just experiment, see what works. How do I select the best things? As I said, initially, I'm just going to find some that have got out of the bag. Well, if we start thinking a bit further through, there's lots of ways you can select the best ones, and I'll show you a couple of other approaches later on. The 3 main approaches in the literature. The first one is based on you ordering how good something was. And then you could choose a number. Maybe you always want to take something out of the top 10 of your population. Just choose a random number between 1 and 10. If you've then got them lined up in a rank, there we go, you've got one of your top 10. There's also another variant called proportional selection, which is based on the idea of a roulette wheel. And we'll try that later on when we see my first weight doesn't work out very well. And another quite simple one is just a tournament selection, where you choose some at random, maybe 3 of them, and just see which is best out of those. That way you don't have to line up the whole population. So sometimes that's computationally quicker. So it just depends what you're doing. And if you can think of a way of doing this, it's probably legitimate. Give it a go. And if no one's done it before, you can probably write an academic paper on it. So get your imaginations going. As I said, do we keep the best ones or not? I'm not going to here. Sweep them away. So my first fitness function, with some horrible Python that's crashed over the end of the line. I'm sure I could have expressed this more simply. But basically, my choice is, and I'll just choose one random item out of these 2 pools of the angle and velocity. Anything that escaped the bag. So I'm just going to see if it's gone over one edge or the other edge of the bag. That is not much use if none of them escape. And I've just told it to run for like 10 generations or something. I've wasted the first one. So that was a daft thing to do, but I did it anyway, before realizing how daft it was. It's simple, and starting simple is good sometimes. Let's just go through how we do the crossover. So if I've got 4 things in my generation with my angle and velocity, and I decide these 2 on either end, V1, theta 1, and V4, theta 4 escaped and the others didn't, select them, and the crossover bit means I take a mum and a dad, and then I can take the velocity from one and the angle from the other. And that way I could have bred 2 children. I think in this I happen to have just taken one of them, so I've taken the first one. You could do 2. You could randomly decide what you're going to do. The astute amongst you will have noticed that I've chosen a problem with just 2 parameters here, so we don't have to start thinking about what might happen if we had more. We'll do that in a bit. I'm making the microphone crackle, sorry. So, code, I've got my choices, and I'm going to build up a new generation of the same size as the last generation. You can vary that as well. Sometimes you want to narrow down things as you go. Sometimes if your problem's not going well and you're not managing to find a solution, it's okay to let the population size increase. I've just kept it steady. Randomly choose a mum, randomly choose a dad. Take the velocity from the mum and the angle from the dad, or was it the other way around? Doesn't matter, can't remember. Slam them into the next generation, then we launch those, see if any escape or not, and rinse and repeat. As I said, we might throw in some mutation. So, given my 1 or 2 new children, I could add a small amount to the velocity. Some people might recognise DWs from some stochastic calculus from a previous paper bag escapology incident. Or we can just change the angle slightly. The reason we're doing that is to just keep exploring the search space. Make sure you don't get stuck in a rut somewhere. Just keep exploring. So, I think I possibly made some bad choices here. Code was, how often do you mutate? Well, I'm just seeing if I've got a number less than a tenth, so I'm giving myself a 10% chance of mutating. You'll tend to find when people are doing genetic algorithms, they decide these kind of things by some experimentation. And given I said this was about machine learning, it's surprising the number of machine learning algorithms that a human runs and goes, oh, that didn't work. Changes all the numbers, does it again, and eventually writes up the one that worked. You don't always get to find out about that tweaking process that happened. Why have I chosen to just move the velocity by like a tenth either way as well? I don't know, I was clearly getting fixated on a tenth at that point. I think I did just play with some numbers and these seem to vaguely work, but as I said, I've forgotten what I did wrong first there. Sometimes as well, if you just want to nudge something slightly instead of pulling something out of a uniform distribution, there are other distributions. If I take a bell curve instead, it's more likely to just move a little bit. And some problems you want to move just a little bit. Other problems it's okay if you jump further. So again, choice is yours, experiment, and the machine's not learnt it, you just played with it, but see what happens. So, putting it all together, the code's relatively simple actually, and that's why I picked this example, because genetic algorithms are quite simple to code up. So I've got some magic numbers. So we can see like how big is each generation, how many times do I go around my for loop, what size is the paper bag. As I said, I don't think the colour's pertinent, which is good. Do something random initially, see what happens, and then we just loop round doing the crossover, the mutation, see how we're going. And we hope it gets better. It doesn't always with my bad fitness function. Moving pictures. So I didn't bother drawing the pictures of all the in-between steps. It was chugging out some numbers to me. As I said, this one doesn't always work very well. So initially, 4 of them got out, yes. And after going around the for loop several times, on this occasion, only 1 of them got out. But it's still out of the paper bag, so I didn't promise it was going to work every time. It worked. This one's quite random because it's just putting the ones that have escaped initially. It's a kind of all or nothing setup. And in this case, it's actually better if we take on board some information, the ones that nearly escaped have a more numerical scale. If I do it again, it'll probably do something completely different. It's very unstable. So this time, 2 of them escaped initially, but it did better afterwards. But still, I've programmed some things out of a paper bag. Let's have a better fitness function. So instead of having the all or nothing, which was the simplest starting case, we can now actually think about how to give a number to describe how good a solution is. And then we can start doing things like the ranking or the roulette wheel selection. And it's quite important, actually, if you consider some of the cases. In this example, I've got 3 things that have got out of my paper bag, and several things that haven't. But for example, on the left-hand side, there are 2 paths that have got quite close, actually, compared to some of the other ones that just kind of gutter along the bottom. So if you imagine a dotted line at either side of the bag, and see where the path crosses that line, that's going to be a number. Y is 0 at the bottom, 10 at the top of the bag, and anything above that's a bonus. I can then give you a fitness function that's a number. And then I could say, I could allow myself to select some of the ones that didn't actually get out of the bag, but nearly got out of the bag. And then I could use more information each time. And that might be better than what I was doing previously. So if I assign a fitness that's just the height where that dotted line is, then I might want to improve things slightly. Having got my fitness function as a number, I could now do something, as I said, like the roulette wheel selection. So if I just got 4 things that escaped, one that got 15 high at that point, so it's out of the bag, because the bag was just 10. And then one that just got 1 high, so it wasn't very good. One that got 6 high, so nearly there. One that got 8 high. If I take the sum of those numbers, which happen to add up to 30, if I choose a number between 0 and 30, that would be like spinning the roulette wheel. It's more likely to end up in the one that's 15, that's really good. But if I got my initial generation where nothing escapes, still be some that got closer than others. So I wouldn't have thrown all of the information away then. I'm more likely to pick the ones that got higher up. That might speed things up and make it slightly more stable and slightly better, which is good. So that's just a case of taking the cumulative probabilities or the cumulative heights. It's not a probability unless it's between 0 and 1, but I didn't need to divide it through by the sum. I can just scale up the random number choice I make to pick the right bit of my roulette wheel, and it should be better. The code could probably do with a tidy up. However, my final observation was I'm doing the selection as every 10th of a second or something. Now, I don't need to do that because I can actually do a tiny bit of algebra and think about it. And instead of going, well, at one point in time it hits here, the next point in time it's here, where did it cross the bag? If I do some interpolation, I'm going to end up thinking that didn't get out the bag, but actually it did. Given I know where it started and how far it is to the edge of the bag, I can back out the y value from that x value. So I did that as well, and that speeds things up, which is always good. Sometimes do some maths with pencil on a bit of paper rather than just hacking. Sometimes works. So I'm going to use a better fitness function, and then we're going to do the one without the interpolation. It's just a bit more stable this way. And slightly quicker. Come on, keyboard. Better? It was definitely a little bit quicker, I reckon. So that's using the better fitness function. And then you can see the initial random choices it made for the pairs of parameters. There actually were several that were quite close to getting out, so it can use the information for those. And then the version where I'm catch the ones rather than doing the linear interpolation, actually see where precisely it got. I got lucky that time. They all came out, yes. I would pretend that happens every time, but it doesn't.
I noticed in this run and the last run that you end up with everything going to one side.
This is something I wish I'd started measuring. That's tending to happen. But every now and again I get some going one way and some going another. But I'm tending to get them finding one solution. And in theory, if you do your genetic algorithms right, it won't necessarily go to one solution. You can find more than one solution. And if you're in a situation where there's more than one right answer, that can work. These do tend to go to one side or the other. Not always.
This one, the first two that escaped both went right, and at the end they all went right.
Yeah.
The last one you had ones going both sides, and they all ended up going left.
Yeah, it'd be interesting to do some measuring of what's actually happening. I'll probably find I've got loads more bugs in my code than I actually realise.
Is that maybe because the angle is the most important feature? Because the bag's quite short, maybe?
Yeah.
So if you increase the height of the bag, then it will become more important the speed at which it gets shot out.
Unless it goes straight up. There's not going to be a linear thing going on.
So then that might be usual for the wider counting thing.
I think actually it would have been quite interesting to graph what happened with some different parameters as I'd gone. And at that point about do they go out one side or the other? And I've kept the bag size the same all the way through this. I've kept gravity the same all the way through this. So there are lots of magic numbers we could play around with here. However, time presses on. So, we talked about this a little bit, but just re-emphasise crossover. And you need a bit of imagination about how to make that work in a more complicated situation, but it's quite obvious here. The mutation, and you need to choose the rates you're doing that at. The selection is about the fitness and the quality, and trying to find the numeric value for the quality is one of those perennial problems that here we are. There are quite a few good books about this, but the actual idea is that simple. Just try something. Try and recombine it, twiddle it around with the knobs, see what happens. Just sit back, go, that didn't work, try something different. Just, sorry. Yeah, and then we started talking about what happens if we change the size of the bag. And the generation size actually makes a difference. I think I experimented around with this, and this was the smallest one that actually appeared to be learning slightly. Well, again, learning's a stretch because I had to choose numbers like the mutation rate and all the rest. So, yeah, magic numbers. Does mean, of course, I've now got a problem where I've got several numbers, like the size of the bag and the number of generations and the number of epochs. And so I've got another load of parameters I'm trying to work out an optimal solution for, which means that I could write a genetic algorithm to do that, which leads you to a whole body of knowledge about meta-heuristics, because as we've already alluded to, the machines aren't really learning, so then it, yes, turtles all the way down. But it is really interesting, it's worth doing. And if you've got a problem that you can't figure out what numbers are optimal, just try something random, maybe something as simple as a genetic algorithm might help you discover some things, especially if it's a huge problem where you can't mathematically work out the best thing to do. Obviously, with the ballistics paper bag example we've just had, we could have done some maths and worked out what angles we needed for which velocities. That depends. The things I've seen these used for, I've used them a little bit in PhD and then just larking around with this kind of stuff. What will happen with a lot of machine learning algorithms and simulations is that some things take a long time. So sometimes you can start off with just be real general to get a feeling for the problem space. and then go, oh, well, look, let's just keep the angle at 75 degrees, and then be more specific and see what happens, get a better feeling for the problem. And then you might find that this velocity is better and then start varying the angle. But sometimes as the first pass, just let it do anything it wants, which is why I called out that I'll put 2 as the lower bound for one of my numbers. I don't know why I'd done that. I thought I was helping, and it would have discovered that the 0 didn't get out. If it hadn't have done, then I've definitely got a bug in my code, and I've got some test cases for that. So it does depend, but if you're doing this for something that's mathematically intractable and you just can't get a handle on what happened, then just let it fly, sit back and see if you can spot some patterns or some clusters, and then explore a bit deeper. So, as I said, I came up with a simple problem there. It's got 2 parameters. You will have observed that if we were starting to look at the width and the height of the paper bag and gravity and all the rest, we've then got more than 2 parameters. So you then, at that point, have to make a choice about where you're going to put the split for the crossover. I could put it 2 points in, take 2 from one and 4 from the other if I've got 6. I could vary it. I could get the algorithm to find out the best place to put the split. Sometimes there's not a best place. Sometimes the problem you're trying to solve has got some parameters that kind of clump together compared to others. I could interleave them. Anything you can think of and code up is something that might be worth trying, but it's going to depend on the problem you're trying to solve. And actually, sometimes we go beyond just having this flat set of parameters. I have a little glance at tree structures in a while. So the main author on this guy called John Holland, worth reading up on. And Goldberg talks about genetic algorithms a lot. There are loads and loads of frameworks for genetic algorithms out there which will cover all the things like different split points, changing mutation rates, changing parameter sizes. But actually, a lot of them are easy enough to code up yourself. But if you want one out of the box, Weka is a Java framework that's got all kinds of machine learning algorithms in. There's some .NET ones, there's some Python ones. Details on the slides for later. If you do want to start moving it towards the tree shapes instead of just the flat genetic algorithm array shape, then Koza is the main author there. And some fascinating stuff in genetic programming, which is way beyond the scope of this, and I can't work out how to use it for paper bag escapology. Right, that was your brief hit-and-run introduction to genetic algorithms. There should be enough there that you can follow what anyone's talking about if you read up on it. And try and code one up yourself. It's quite simple. So, let's go back in history. If the genetic algorithms were happening mainly from the 90s, take a step back, reaching right back towards Turing, really, and talking about artificial intelligence and artificial life as well, which had led him into things like looking at zebra stripes and trying to build something that would play chess and similar. This encompasses lots of different things. We're talking about software. Start doing you can evolve some things with hardware. I like my sci-fi as well, so the wetware phrase sneaks in there. And I noticed Andre is going to tell us about fastware as well, so it's that ware on the end of almost anything. So, the artificial life stuff, my understanding from reading around a bit is it dates back to around von Neumann trying to build, well, he was trying to come up with a small set of instructions that you got something that's self-replicating and doing the kind of thing we just did there, that mutation and explore the space. And actually, I think some of this predates solidifying the ideas of DNA and how that actually works, and possibly laid the foundations for people to be able to think like that with some simple rules, you can encode some behaviours and get all kinds of complicated things happening later on. Holland then picked up that idea and just narrowed it down to the genetic algorithms. So gone backwards in time. A lot of this was happening in the 50s. There was a lot of paranoia going on, which nothing ever changes. A lot of this was to do with cryptography and perennial problems about trying to come out with better communication systems and security. And always, each time I read about this, I end up straight back into these feedback shift registers. Always. And this Ulam guy who cropped up last year. Someone else who doesn't get a mention very often, who was working in the same sort of area at the same sort of time when no one was looking, was doing his own personal pet project on his work computer. We'd never do that, would we? Yeah, silence from everyone. Good, good. He was trying to build a similar thing of artificial life, which he called numeric organisms. Only he emulated the random numbers just by shuffling playing cards, but just thought he needed a mention because he often gets left out of the literature. Varaceli. So we talked about the hard AI earlier on. It's funny, I thought people had stopped worrying about that kind of thing. And then Stephen Hawking started talking about, AI panic. What happens if we do build machines that drive cars or the drones? It was interesting. We went for a patch where instead of trying to build artificial creatures, just trying to draw parallels with what nature was doing to solve some real problems instead. So solving real problems and building more powerful machines instead of trying to create a man or an Ubermensch or similar. But then Stephen Hawking started pulling it back round again. Yeah, just that perennial thing of like Frankenstein's monster. What are we messing with here? Well, if we're just trying to emulate what happens in nature to give us inspiration of a different approach for solving a problem, that's quite cool. And some of these solve optimization problems, like I said, some of the genetic algorithms then solve the problem of what parameters to use for your genetic algorithm. And should we be scared of machines? Or do we need to worry about the people that actually exist at the moment? I mentioned like self-driving cars. What happens if someone hacks into one of them? I went to a talk a few weeks ago, and there's apparently electronic skateboards are a thing which you can control with Bluetooth or wireless from your phone. And the guy was taking great delight in explaining how he'd hacked into one of those. It was tremendous fun. What are people doing with all the data that they're gathering on us? If you're getting 24 hours a day footage from CCTV camera, you then need a machine to start analysing it. I've got myself in a feedback loop here. So I'm not afraid of the machine. I'm not afraid of people either. Anything can be bad or good. It just depends. But just a thing. Promise I'm not going to build T2 or Frankenstein's monster today. As I said, some of these things, if we're just borrowing from nature-inspired stuff, you can see these being used in a variety of places. If you're modelling something growing, for example, the sprawl of a city, you can then start predicting where you might need to build new schools and new hospitals. And that you're unlikely to come out of a mathematical model in advance that's right, but you can tweak things as you go and go, actually, that does seem to be matching what's happening just with some simple rules, rather than a maths formula. And there's other examples of computers trying to write music and do art as well, each to their own. I'm following a random bot on Twitter that's generating some sometimes beautiful and sometimes hideous things just with some trig functions and some caps and floors and things. It's sometimes nice, sometimes not. Evolvable hardware was a thing as well, and that ties in with some of the genetic programming that was happening earlier. Though there's been some resounding success there, but I think some of the companies that have done it, back to our Frankenstein's monster just now, feel slightly twitchy about selling some circuit boards that the machines created if they don't 100% understand how it actually works. So it depends what you're trying to do. But there are loads of real-world uses and applications of this, not just one silly toy problems. Just one small aside, I'm going to look at artificial life by building things up from some rules. But I've seen examples of people using more complicated things like neural networks here. Don't know if anyone remembers creatures. It's based on a screensaver from years ago that you could interact with a bit and it learned. That still seems to be out there. I'm not going to do I'm not going to do the neural networks today. And Steve Grand is a man who's also, he invented the creatures. I don't know if anyone's come across Growing Up with Lucy. If you find the book, read it. He was building a robot there, so it's maybe straying more towards the hard AI stuff, actually building a machine that could see and interact with its environment. He moans loads about servos and them being too heavy and it falling over, but it's a real good read. However, back to what I'm supposed to be talking about. I guess Conway's game of life is one of the artificial life things that most of us have heard of. Heard of? Yes? Yeah, most of us. And that the classic glider shape just crops up on so much hacker and computing literature. It's amazing. Got 4 simple rules. I'll leave you to go away and just work through yourself by colouring in some blobs to see what happens. But basically something's coloured in, which signifies alive, or is not coloured in, which signifies dead. And the next state depends on the state of its neighbours. The idea here is that if you've got overpopulation, things die off. And under some certain circumstances, some things can flourish. You can possibly see how that might work if you're trying to model like urban sprawl or similar. So just 4 rules and some amazing things happen. So my hair that's doing that might be. And again, I'm following Conway's life on Twitter, and every now and again they find some new exciting thing, which is really cool. Each to their own. The train of thought that ended up here, I heard Michael Feathers talking a while ago, and somebody asking, what's the new thing that's coming up? And Kaplan might have mentioned things about microservices recently, but he mentioned he'd recently seen someone code up the game of life in APL, which I'm not going to pretend to understand properly, though I've had a little play with variants like Q that are based on it. And yeah, I'll leave you to go away and try and figure out what's going on in there. Promise I won't do that, I'm going to do some C++ instead. So, there are 3 main categories of things that fall out of these, just 4 simple rules. Sometimes you'll get some of your dots will just stay still. Sometimes you'll get a pattern that, well, the simplest one is 3 dots vertically, and the next step, if you think it through with pen and paper, will give you 3 dots horizontally and back again. So it's oscillating with a period of 2. They have found some oscillators with much larger than 100 period. So it stays where it is. And eventually, after well over 100 steps, gets back where it started. Interestingly to me at the moment is, or until a few days ago, as far as I'm aware, no one's found one with a period of 19, 23, 38, or 41. So this is your chance to shine if you could. And I started wondering whether mathematically you could prove that wasn't possible, but then I had a pint of Guinness, so I'll pick one up later on. But just interesting little thing, just from these 4 rules, lots of fascinating questions. Now, aside from the things that stay still, the things that oscillate in place, you get some things like the glider we saw in the last one that just moves. And those spaceships, and the catalogue that I mentioned that I'm following on Twitter has got loads of them. And you can download some code to your own machine, and it can go off and explore, and it'll report back if it finds something new. So, after my horrible Python last time, I did a tiny bit of C++, I came across something called Simple Fast Media Library, which is an open source thing for drawing some pictures quite quickly and easily in 2 dimensions. So we get a window, and if it's closed. We could check for key presses if we wanted. Then we draw what we want to draw and leave it to it. So quite simple to just bolt your code in there. So I shall use that. Some code. Well, basically, I've got my 4 rules. As long as I can see if someone's neighbour's alive or dead, I can work out what state it needs to be in next. which all seemed quite simple. And then I've done some evil and I need to revisit this code, but it was good enough to get it working. First, I'm going to have a width and a height. I didn't think this through properly, and we'll see what goes wrong in a moment. And I thought, well, it's alive or dead, and I want to put this in a container. And vector balls aren't really containers, and they're about to be deprecated, so never use vector ball. I've also constrained it at this point, and I'm never going to find an oscillator with a period of over 100 with the way I've got this set up. And I'm actually not going to manage to program my way out of a paper bag until I step back and realise what a silly thing I've done. You might have noticed where this is going. Yes. So, we all know vector ball's evil. Good. If you thought that was evil, don't look. I understand that at XP 2016, someone's going to code up Conway's game of life about the ifs or elses. And I rather think I should probably go, having done that. I'm very sorry. The code is on GitHub, but I suggest you do it yourself. It'll be much neater than mine. So, note to self, do a demo. One moment. Leave it to it for a bit. Remember, we're trying to program our way out of a paper bag here. Remember, I said I'd chosen a width and a height. Got some stable patterns. We've got some oscillators. I've assumed that if we get to the edge of the width or the height, everything around us is irrelevant. If above the height of the paper bag is irrelevant, I can't get out of the paper bag. Which was a bit of an oversight, but it's good to share your mistakes and learn from each other. Bringing in the edge conditions made it stabilize quite quickly. So what if I made it wrap around the edges so I can go that way or that way, and it joins up? Almost like a kind of spherical paper bag, but it will still look square, it's just a projection. I'm going to do that. I'm going to let it wrap round the edges. The astute among you may have observed that round the left wraps to round the right, and the top wraps round to the bottom. So it doesn't stabilize as quickly, but it still doesn't get out.
How could it get out?
Exactly. What have I done? Or I could make the world slightly taller than the paper bag. Then some of them might get out. That would have been more sensible. Go on. Third time lucky. Some of them are out. What would have been far better is not to have used the vector of ball and actually thought through properly how to let things go anywhere in the entire world. Possibly not through the sides of the paper bag. Not clear. It wasn't a very clear specification when my colleague said that guy couldn't even program his way out of a paper bag. But yeah, I think I should revisit this and have a very different data structure so it can explore the entire world. But some of them are out. Sometimes there's a glider, which makes me happy. just from the 4 simple rules as well, actually. It can be quite mesmerising. It's more mesmerising without the paper bag in the way, or the whole of space to explore. Anyway, get the general idea. Some of them are out. Don't use vector ball and think about what you're about to do. So yeah, some stabilised things. There was a glider in that one, but sometimes happens. We said all that. Now, not everything got out of the paper bag, so I started wondering to myself if I could use a genetic algorithm to mutate the rules and make them more likely to escape. And I thought I probably could, but given I hadn't got a decent enough data structure to let things out properly, I'd leave that as an exercise for the listener. But it did get me thinking about other things I could play with. Now, Conway's game of life is one of the classic cellular automaton things. So just to mention there are loads of other variants, and you can make one up yourself if you wanted to, but lots of other interesting ones out there. Before we go much further, actually some of these ideas of doing something random and seeing what happens are pertinent to testing. Some of us test things just manually. Some of us will have some unit tests. Quite like having some unit tests, even though certain keynote speakers might be railing against them at the moment. Integration tests. Even some kind of static analysis is you're verifying or testing your code. But just touch on 3 things here, just quickly. Zoom through them, but there's some random things there that can be useful. And so, I mentioned in the list mutation testing. I think someone's talking about mutation testing in Python tomorrow, if anyone's interested. I'll give you just a glimpse of what it's about. And also mentioned property-based testing. And again, I'll give you a little glimpse of what that's about. And just coincidentally, someone's talking about it at the moment. It seems to be something people are thinking about. How else can we test our code? Can we get the computers to do some of this for us? Explore the search space, find out if it works or not. So, property-based testing. We noticed so far a lot of my code has some magic numbers in. And I bet often you look at one of your unit test cases and it's got a magic number in. Because it doesn't matter what that number actually is, so you just whatever or some number or something. Property-based testing, instead of you hand-rolling one exemplar as a unit test, you tell it a property you want to hold true. If the velocity is 0, my ballistic never gets out the paper bag. And then it can generate loads and loads of different angles for you. And you might find you hadn't thought through one particular combination or edge case, and then you could turn that into maybe a unit test and start fixing things that way. So property-based testing, it just randomly generates things and reports back if it finds some mistakes that violate the property. It's pretty cool. It's got its roots in Haskell, but there are variants in various languages. Next one. Okay, if my unit tests or integration tests or whatever are my watchmen, my guards for the quality of my code, how do I know how good those tests are? Who watches the watchman? What you could do, and this is what mutation testing does, is it mutates your code and then reruns the tests. And if your tests pass, is that good? So, write some tests first. This won't work if you haven't got any tests. You need some tests and run them. The framework will make changes to your code, and we say that the mutants usually go against the specification, so you get people writing about kill all mutants when they write this up. Can't help themselves. Do things like change a greater than for a less than, put a not in somewhere, or bail out of a loop early, or anything like that. So I tried running this over the genetic algorithms tests I found a Python version somewhere. Before I do that, we just said, is it if you change the code and your tests still pass, is that bad? Well, it depends what we're actually up to, and sometimes we are deliberately changing the code ourselves to try and make it better. But there's a high chance if we're doing TDD and we're refactoring. But if something's randomly slapping knots in your code and the tests all still pass, then, well, maybe that code path's never used. You can delete loads and loads of code, so you found one good thing out anyway. You just still need to think that fitness idea. So I tried this pi-mu tester on my GA tests, and it didn't find any mutants that survived. So it's tried inserting some knots in various places or bailing out of loops early. And that's my hair getting in the way. Should have tied it back. Gave me slightly more confidence in my tests. Now, that version was just taking the code of the Python and changing the file. You can be a bit more sophisticated than this. You start using the syntax tree. And I think the Python mutation testing that's going to be demoed here is something probably a bit more sophisticated. And with Clang, you can do this in C++ as well, though I've not had time to explore this properly. But as soon as you've got syntax tree, and you're not just making random textual changes to a file, you understand what's going on. You can flush things out. Now, hang on. I mentioned the genetic programming earlier, so we can see what mutation might be like with a tree structure. I start thinking about language as a tree structure, and I said, could we automate everything, including the code generation? You can build things up with a crossover as well, and doing something like genetic algorithms. Got a syntax tree. We saw what crossover meant in the genetic algorithm context. And this is what genetic programming is doing. I did start sticking my nose into this in my PhD and didn't have time to follow it up, but one day I'll write some code that writes the code for me, because that's the obvious thing to do. Well, just quite simple. Tree, choose a point, cut one bit off from one, and join this up with the other one. As soon as you've got a syntax tree, well, you can still end up with things that are syntactically invalid. But that's okay, because you can either kill off the bad children or your fitness function to find that out. But you can automatically generate code as soon as you've got that structure going on. Mutate it, solve a problem. So, just some more notes on the genetic programming if you want. A side point recently that I think Dr. Chris is around somewhere, and he's spoken at the ACCU conference before about search-based software engineering, where you don't just leave the machines to create Frankenstein's monster for you. He's been getting some people to inspect the outputs, and what he's described as a human in the loop, so they have some input to the fitness function. Though you could argue if the machines are generating the code, then a human never needs to even look at it. They could just drop right down to machine code or something. But he's been doing some quite interesting stuff. Complete distraction from me coding my way out of the paper bag. So, as I said, let's bring my genetic algorithms and cellular automaton together. The simplest form of cellular automaton, I mean, we saw the 4 rules with Conway's game of life, but you're down to, you've got some cells, and if instead of me exploring the whole of space because I got in a mess with my vector ball and ran out of world, and there we go. If I imagine a bag however many units wide, and see what state I'm in initially, and then I have a rule that gives me the next state, which I then just draw up 1 unit up, and then see what my rule gives me for the following state, and just let it go up. We just see how many things I've got alive at the top of the bag, and if some of them are alive, then they're out. How am I going to do this? Well, I could choose the rules and the starting cell, but then the machines learnt nothing. So I could try and use some kind of genetic algorithm to either evolve the rules or the starting cells, or both, for me. So I mean, I could have a rule that just says flip the bits. So 1 for on, 0 for off. Rule just flips the bits each time. Now mathematically then I could work out, depending on whether the bag was a even or odd height, what the best thing to do is. I could, the simplest case, and I'm going to do this, is have a rule that just keeps it the same. And then I could ask what's the best rule for a given cell. I started, as I tried to think this through, thinking I can't find a way to programmatically say what's the best rule. Maybe I need to say it looks prettiest or something, or I need the human in the loop, so I didn't think that through properly. So, same sort of algos we had for the genetic algorithms before. We're going to start with something random. I need an idea of fitness. We already said, well, let's just see how many cells are alive at the top of the bag. And I'm going to do some mutation and crossover, maybe report the best each time. So just randomly set up a starting cell. I don't know whether I want things equally alive or dead. I can play with the distribution I use there to change what happens, but just basically I'm going to build up some cells. Some are alive, some are dead. If I used a uniform distribution, just 0 and 1, then equally likely, and I can fiddle with this if I want. This is what I've actually used. Shouldn't be doing that, as discussed. We don't want vectors balls. I can change the distribution to, say, a Bernoulli distribution to make things more likely to be dead or alive, depending. Lots of options. So I can set up a vector ball of on or off. That's easy. What's a rule? Well, it takes in a arrangement of cells and tells you what the next one is. Simple. How am I going to generate that programmatically? Well, conveniently, we just had something that tells me a cell, and it doesn't really need to bear any relation to what the input was, as long as I remember them in some kind of lookup table, so that was handy. Now, I could try and generate rules for every possible combination of cell, but as I started doing this, it occurred to me that I completely lost the plot. I was unlikely to get any of those cells, and I could maybe just generate them on demand as I went. That would be much more sensible. Lots of words there. So, just got some kind of lookup table, maybe a map or something. If that cell's already in there, then I know what cell it maps to. If it's not, generate another one. That'll work. How do I do crossover with my rules? Well, if we've got one set of rules and another set of rules, rip them in half, slam them together, make a new map. Except I just said I'd do the rules on demand, so I haven't thought this through. How do I mutate? Simple, just find one row in my map and go, just make a new one. So to see how to do that, we need the fitness as well. We remember this from before. Yeah. How do I know if my rule's good or not? You could do it in terms of does it look pretty or something, but I want my pint of Guinness, so we won't do that. If you'd like to do that, then please do write it up and send it in. Let's keep it simple. For a given rule, I'm going to find the best starting cell. That's far saner. And I can do the crossover in a similar way there. Again, I've just got an array of off or on. So choose somewhere to slice it, maybe in the middle, join them together. I can mutate it by flipping the bits. And the machine's mission is to find the best starting cell for a given rule, where better means more cells are on at the top above the bag. So, this slide's a bit of a car crash, but my rule is going to take a cell and return the same cell. We can do this in our heads. We just want all the bits to be on. That would be great. I'll randomly fill in some initial configuration, and then we just run the trial, which is them chugging up the bag one line at a time, cross over the starting cells, maybe mutate some of them, and hopefully it will discover that if I've got my rule of stays the same, that it should turn all the bits on to begin with. Now, we saw the simple example earlier just had two parameters, the angle and the velocity. This one I'm going to have more than 2 cells. So for example, if I had 4 cells, I had mum with 3 cells on, dad with 3 cells on, and I cut them in half and joined the left from one and the right from the other, I ended up with a child that's worse than the parents. Now the fitness could flush this out. Now some genetic algorithms choose to kill off the bad children, which, remember, this is just an algorithm, so that's okay, so that's what I've decided to do. But just the point there, the shape of the problem you're trying to solve, it depends what you do, where you put the crossover point, just experiment. Fitness, we've already said, we'll just see how many are alive at the top. This one, instead of sweeping away all the initial starting cells I've tried, I'm going to keep the best one each time to speed things up so I can get my pint of Guinness. But you can play with that. You could just kill off the worst ones, up to you. Mutation, again, you've got to decide how often to mutate things. And I decided that 50% of the time is okay. And I'll just flip one of the bits somewhere in the length of the cell, the cells I'm looking at. And it does sometimes find the best. So we're going to start with, well, it's just going to report its best guess at how to keep them the same and keep most of them on. And we'll see them zooming up. Hopefully I've got a reminder to myself to do a demo. I do. Oh, that's good. So the numbers are chugging how many alive, and we got 31 out of 32 there. And some of them are out of the bag. Again, that was a nice simple example. I still don't know what best rule would actually mean. I hadn't thought that through properly. So there are lots of things I can vary here. I need to decide the population size. I did that by some experimentation. I think I started with about 25. Can't go much below that, otherwise it doesn't find them. The mutation rate, and again, we've got all the magic numbers, and I'll refer you to the previous slide that says if that happens, you either need to experiment yourself or start using something like a genetic algorithm to find out the best parameters. But just playing around with it yourself and seeing what happens often works. Said it, yeah, remaking the same point. All these magic numbers. You can just recurse and do the meta heuristics on this. Machines haven't learnt anything. That's the thing that we should take away from today about machine learning is they haven't really learnt anything. They're just doing what they're told sometimes. So we talked about if I have random rules, I can't work out what the best rule is. We can still try a random rule and a random starting cell and see what happens. Wrong. And I'll put the caps lock on, that's silly. So this has just evolved a random rule and a random starting cell. A different pattern every time. And then, like I said, we can start experimenting with which ones we like the look of. When I did that, I looked at it and thought, why have I made them cyan instead of green, for example? And what if they went down instead of up? We've already had the matrix mentioned today and spoons earlier on. There's clearly a meme doing the rounds at the moment. Set me thinking about the matrix. I pulled the quote from there, a world where anything's possible. But just with the 4 simple rules from Conway's Game of Life, you can get some quite big, interesting things going on. And just with the simple idea of the crossover, the mutation, and the fitness, you can start doing some quite powerful and useful things and solve some real-world problems rather than larking around with paper bags as I've been doing. Including seeing if your test's really good, including generating code for you. All kinds of things, actually. And I personally like real simple things. Know about neural networks as well, and they involve some quite heavy lifting mathematically. But a surprising number of the machine learning algorithms and the artificial life things are really simple. And I like that. I like the simplicity there. At that point, I'm kind of done. So we've looked at genetic algorithms. Try something random initially, and then do the crossover and mutation. Have a clear idea of what fitness means. And we do that when we're coding anyway. So we know what we're trying to achieve. And if you can't assess whether your code does what's required or not, then your requirements are as vague as the can you program your way out of a paper bag. So refuse to do it and get clarity over what's required. It was quite fun crossing over the 2 different memes, and that's a good way of exploring things as well, trying different paradigms, different ways of doing things, seeing how you can learn from one and improve the other. And yeah, randomness is really quite powerful. And even things we do as humans, like the scratch refactoring, just try it, take it to pieces, try and put it back together, see what happens, explore. Own up to your mistakes. I know I do, that's important. And yeah, we just need this idea of what's good. That's really important, and it's really hard to quantify. But you can try. And that's it really. Like that automatic code generation, dream. And automatic editorial generation, but that's a different story. If you do want to write for Overload, you're more than welcome. And my hair's in the way of the mic again. I'm done. If anyone's got any questions, that's fine. Sorry.
So how important is the assumption of continuity? Because for instance, in this case, you always have something that if you perturb the initial state a bit, you will get some kind of cost or some, I don't know, this what is good would be very close, or at least bounded by the upper. So, but if you have some code, for instance, which is a sequence of some instructions, if you perturb it a bit, it will not get close at all.
Yes.
To the problem. So it kind of seems to me that this is the basic assumption that you make.
So there was a question earlier, I can't remember precisely what it was, and I said it depends. It depends what you're doing, and that's the trouble with why this is not really machine learning. You need to choose a mutation rate, and you'll find certain types of problems, and the mutation rate's keeping you exploring as much of the search space as possible. But you can do things like you can observe if the fitness is going down or staying stable, and you can change the mutation rate. You can turn it down, turn it off for a while sometimes. So for some problems, you need to build that in, and that'll stop you like doing something where you jump into a discontinuity if you turn it off. So you sometimes need to be adapting what you do. But I mean, you're quite right. As soon as you start messing around with the syntax tree, you can end up with things that are completely invalid. But then again, your fitness function will kill those off if you've coded it up right, but it might take longer. So.
Yeah, but that's exactly the point. So if you have some problems, for instance, so you want to find a program which computes some, I don't know, find some minimum.
Mm-hmm.
So you have a sequence of instructions. So whatever you do, if you perturb it a bit, it doesn't move anywhere like continuously. It just jumps all around unless when you get the right solution.
Sure.
If you perturb it just a bit, it's not even close.
Yeah.
That's the problem, right? Unless you put some set of algorithms to your code, so that basically you restrict the decisions for the computer to select among those algorithms. So that means that the computer can't be any smarter than you are.
Sure. So genetic algorithms aren't always the best way to solve problems. For some optimization problems, something more like neural networks might be better. Second, if you try something and you observe the fitness is being very volatile, as it was in my first example with the ballistics going out the paper bag, where I'd used the real rubbish fitness function. Sometimes all of them go out, sometimes none of them go out in the end. After the average and the volatility over a few runs, if it's really volatile, you're doing it wrong. Your parameters are wrong, or the genetic algorithms aren't going to work, or fitness functions wrong, or like you said, if you've got a discontinuity, then you're just randomly searching around. There's some algorithms that just randomly search around and don't do the crossover. Sometimes the crossover's a mad thing to do. And I do have a gut feeling that by doing the crossover with the velocity and the angle that I did, I was probably doing something slightly silly, because the two of them are tied together. And actually that problem I could solve mathematically. But yeah, it won't work for everything. But if you do 10 runs and sometimes it gets one solution and the rest of the time it doesn't get any, then it's not working. Unless one solution was good enough for your problem. So it depends. But you've got a point. If you've got something that's a continuous curve, then you can just nudge a little bit, and that might be interesting. But if you've got big jumps somewhere, then that might be, you might want to jump somewhere else. You might not. It's going to depend. I think we need to work through some specific examples.
We have a zero measure to get to the actual solution. So that
Yeah. We should probably sketch out some examples on a beer mat over a pint in a moment. Any more questions? Oh,
Just to check on this too, so the genetic algorithm you showed, it was essentially stateless, it only kept the generation itself. So the
Yeah.
algorithm itself didn't learn, it's just a bunch of rules. And
yes, yeah.
Is it how, the definition of genetic algorithms, they're
So,
always stateless?
My second one, I kept one of the better ones. But you could still do that. You could take the previous generation and build the new one, throw away everything you learnt before, but keep the best one. So, okay, now I'm thinking more about functional programming and state, but you sometimes will remember the state from the last one. Sometimes you'll keep the previous generation, you'll just kill off the worst ones, the lower tenth or half of them. So you can play with it and see what happens, but the simplest ones, just throw them all away and start again each time. But that's something you can play with. There's no one right way to do it. It's just try it, see what happens. I think there's a question over there.
How important is the initial sampling in terms of how you reach a solution?
I missed the first words of that. How?
So how important is the initial sampling you do in terms of like either the speed of reaching a solution or the quality of the solution?
Right, so we're setting something random up initially. How important is that? In theory, I mean, I was worrying when I was trying to generate the rules, I thought I can't even tell the way I've written the code, which I didn't show you, but it is on GitHub. I can't even tell where I can possibly get all the rules. But the mutation will theoretically move you into any possible space. That might mean that if you haven't got a large enough sample size, you might need to do more mutation to cover possible things. But if you do that, that might mean you're just kind of flailing around. So I'll tend to just do a population of about 5 for most problems and see what happens, just to see if it crashes horribly or something embarrassing. And then I'll leave it chugging with loads more. And then you can do some other genetic algorithms, like I said, to step down. But the samples I've done here, I went down to as few as I could that were going to demonstrate something, just because it was quicker and 90 minutes goes surprisingly quickly. Just try it and see what happens, but often it's worth just doing a very small sample first, just to see what happens, to flush out some silliness you might have bolted in there. But you tend to need quite large populations, and some of these chugging on real problems need an amount of time, and that's why there's the distributed Python version, and you want lots of machines if you want to try loads of things and see what happens. Try it, see what happens. And it does depend on what the problem is. And sometimes you can do a bit of maths first to get a sense. And sometimes you're completely wrong, even though the maths is telling you something, because you missed an important aspect of the problem. No one right answer. Okay. Oh, one more.
Just to comment on that, I use genetic algorithms to solve quite big areas of combinatorial problems.
Wow.
If I start with completely random solutions, they just never converge because the search space is just too large.
Yes.
So that I actually use heuristics to generate randomness and heuristics to generate a population of vaguely sensible solutions to start things off.
Yes.
So I mean, when you've got small problems like the ones you've illustrated, you can have randomness
Sure.
It's fine, or you've got really nasty, big, hairy problems, you need something better than that.
Yeah, that's obviously something I should have mentioned. If we step things up, if you've got an instinct on, well, I suspect this kind of thing will work. Like a travelling salesman, give it a heuristic of go to the nearest one each time, or you've got an intractable maths problem, but you can simplify some of it and go, oh, it's going to be approximately y equals x plus 2. You can put some pre-chosen things into your initial population, and that'll just guide it a bit more. Yeah, but real life problem's far bigger, and it's loads of fun to play with, but hopefully just that little sample of the simple toy problem's enough to get you just thinking about some of the things that are out there. Okay, I think I'm done. Thank you.